Okay, so let's get going. Welcome to the talk, everyone. Is this which right one? No. Looks like we have a slight technical difficulty here. This one, okay, I'm using the wrong one. This was apparently a decoy. Excellent, okay. So I'm Carl Steinbach. I'm an engineer at CitusDB. I'm also a committer and a member of the Apache Hive PMC. And I've been writing software for close to 10 years at this point, and I've spent my entire professional career working at different enterprise software companies. And at those companies, I've been pretty focused on doing stuff related to data and databases. So I started at Oracle, where I worked in the server tech group on the Oracle server. I spent a couple years afterwards at NetApp, where I worked on storage security products. I was at Informatica for a while, where I worked on ETL software. And most recently, I was one of the early engineers at Cloudera, where I was the team lead for the Hive team. And I've included my Twitter ID there so that folks, can tweet snarky comments about this presentation while it's happening, in real time. Anyway, this talk is about a new type of distributed analytic database. And I think it's reasonable to ask, databases have been around at this point for close to 40 years. The System R paper was published in 1974. And you could sort of expect that at this point, maybe this whole idea is played out, at least in terms of new developments. But what's happened, and I think what's important to appreciate is that databases, the raw material that they process is data, and that data is stored on a file system or a storage system. And there's been a radical change in enterprise storage systems over the past couple of years in the form of HDFS. And databases are inherently tied to the underlying storage system. And they make a lot of assumptions about the behavior of that storage system. And these assumptions end up appearing in a multitude of different places in the architecture of the database. And since HDFS has been introduced, and since it's so radically different from what has sort of been typical of enterprise storage systems up to this point, it's really necessary to redesign the database that sits on top of it. And it's this new class of analytic databases that I'm going to talk about today. So I've given versions of this talk a couple times before, and I've learned from experience that it's a good idea to clarify up front what an analytic database is. A lot of people, when they hear database, they automatically think of an OLTP database, which is what people typically use, let's say, for a database-backed website or things like that. And that's a transaction-oriented, row at a time, insert, update, delete style of database. What we're talking about in terms of an analytic database is OLAP, where it's online analytical processing. And this is a database that's not particularly transaction-oriented. Some of them don't even support transactions at all. Many of them don't support row-level operations. Instead, what you expect with an analytic database is the ability to basically take data, split it into dimensions, and then be able to ask questions about the data. For example, let's say that I have records of things that were sold at a big box store over the past month. Perhaps I want to know what the most popular product was, or I want to know, given a sliding window of a 2-day period, which 2-day period accounted for the largest amount of sales. Those kinds of questions, and in particular the kind of questions that we find that enterprise organizations, businesses want to answer, are the types of things that you would use an analytic database for. So the other important thing to understand about analytic databases is that the things that sort of affect the performance of an analytic database are very different from OLTP databases. With OLTP databases, one of the limiting factors for performance is how effectively or efficiently you handle transactions. With analytic databases, the performance limiting factor is most often your I/O bandwidth. Because when you're applying a query in an analytic database, typically it's a sequential table scan. You're probably looking at the entire table or some segment thereof. And first order, sort of the major thing that impacts performance is just how quickly you can pull data off of the underlying storage system into the database for analysis. So we've seen that most of the advances in analytic databases have focused on different techniques for working around that problem. Columnar or column-oriented databases are an example of that. The idea is that if you organize your data into columns instead of rows and you push filters down to the underlying storage layer, you can, in effect, avoid pulling out columns that you don't need to read. So you alleviate that pipe or the bottleneck sitting in the middle. So I mentioned that HDFS represents a big change for enterprise storage, and I think to appreciate that, it's important to, first of all, talk a little bit about what enterprise organizations have been using up to this point. So this is kind of a diagram, a gross oversimplification of the enterprise storage model that people have been using for the last 20 years. And typically, you walk into a data center and you expect to see, let's say, on one side, racks of disks, connected by controllers, and this may be a NAS system, or if you need better performance, you would use something like a SAN. And then on the other side, you're going to have clients of the storage system, and these are the nodes where the actual work is done. The problem with this architecture is that you have basically on one side an island of worker or compute nodes, and on the other an island of storage nodes. In order for the workers to do any work, they need to first of all pull the data from the other side of the room. And this is fine, I mean, when you initially set up your system, but as you try to scale out the client tiers, you have more clients pulling data off the storage tier, they saturate that pipe that sits in between. Or as you add more storage to your storage tier, you have to basically increase the connections or increase the routers that sit between. And this becomes prohibitively expensive. So expensive that most organizations faced with this issue basically have systems in place that age out their data. So they have online operational data, and then they have historical data that they write off to tape, they put it on a truck, the truck drives to a cave, and it languishes there forever. So this was basically the problem that engineers at Google were faced with about 10 years ago. And they were working on their search engine, and in order to basically power the search engine, they needed to do a big crawl of the web at that time, generate a massive data set, and from that massive data set, generate an inverted index, which they would use for their search engine. And they knew that if they tried to rely on a traditional enterprise storage system, that first of all, they would go bankrupt pretty quickly. And probably before they went bankrupt, they would just reach a point where they couldn't scale it anymore. So they needed a better solution. And the way that they reached that better solution was by sort of reimagining what a file system meant. And I think file system in the context of systems engineering is a very loaded word. As soon as you say file system, people have a list of things that means. It means a system where I can do a random read, I can do a random write, I can seek backwards in a file, forwards in a file. When I open a file, I expect to be able to read or start reading bytes out of that file very quickly with low latency. And to design GFS, they went through that list and they threw out all of the things that they knew that they didn't need. They knew that they did not need to be able to do random reads. They knew that random writes weren't particularly important. They were going to be writing into this file system in very large chunks, and they were going to be reading out of the file system in very large chunks. And once a file was written in, they didn't need to modify it until it was tossed or deleted. And what they ended up with was a system that could scale to petabytes of data and support very large streaming reads. And I think it's also interesting to sort of think that this paper that described GFS was published in 2003. And if you look at the paper with just the information that was contained in it, you ask the problem, does this really solve the scaling problem? And I think the answer is no. Because fundamentally, if you go on what was just described there, they didn't challenge the whole client-server separation, the idea that you have clients of the storage system and then the storage system itself with some sort of network interconnect in between. And it wasn't until a year later when the MapReduce paper was published that sort of the missing piece of the puzzle fell into place. Because it was in that paper where they explained that if you take this distributed file system and you eliminate the client layer, you effectively take the clients and you merge them into the storage layer, the pipe connecting the two disappears, and the bottleneck between those two layers disappears. And that's sort of the core idea of GFS and MapReduce, and it's the core idea of Hadoop. The concept that instead of pulling the data over to the work, you take the work and you push it over to the data. So after these papers were published, Doug Cutting and Mike Caffarella, who had been working on a project called Nutch, which their goal was to basically build an open source search engine, they read these papers and they realized pretty quickly that they needed something like GFS, and they needed something like MapReduce in order to be able to build this system. So that was the genesis of the Hadoop project. And that's where HDFS and the open source implementation of MapReduce came from. And in the past 5 years, we've seen Hadoop become quite popular with enterprise organizations. It started with big internet companies like Yahoo and Facebook, who were the early adopters. But since then, it's proliferated out from there. And in that period, I think we've gotten a good opportunity to learn, what's good about Hadoop and what's bad about Hadoop. And on the good side, and I think probably its most important contribution, especially to enterprise organizations, is the way that it's commoditized enterprise storage. I mean, it basically says that you can build a petabyte scale storage system by gluing commodity server components together. And it's really changed the way that enterprises manage their data, because since the cost of a terabyte of data has been reduced so dramatically, data that used to be aged out, which used to be written off to tape and essentially forgotten about, is now kept on site, and companies have found that they can derive insights from it. And at the same time, I think also Hadoop has introduced a level of flexibility that wasn't available in the past. In the past, your typical, let's say, enterprise data center basically consisted of a storage system and a database. And before you could analyze the data, you had to first of all load the data into the database. You had to effectively convert it from the ingest format, let's say a log file or something like that, into the internal format of the database before the database could actually use it. And this was, first of all, a time-consuming step. It could take an hour, it could take a day, maybe a couple of days, depending on how much data you're trying to load. And it was also sort of a high-stakes game, because before you could load the data, you had to decide on a schema. You had to model the data. And the problem with that is if you made a mistake, you'd have to go through the whole process again. So there evolved this whole sort of like hierarchy of people involved in the process. You couldn't load the data yourself. You had to have the DBA do that. And the DBA wanted to make very certain that you had modeled the data correctly, because he didn't want to, or she didn't want to be in a position 3 days later of finding out, oh, well, we've loaded a couple terabytes of data, but it turns out the schema is broken. So let's go through this process again. So there was both there was technical latency in terms of the hardware and the software systems involved, and there was human latency. And Hadoop basically says, it's changed that equation to the point where as soon as data lands in HDFS in any format, you can start analyzing it. So that's been a tremendous change. On the other hand, though, the past 5 years have also given us a chance to learn about some of the shortcomings or drawbacks of Hadoop. And I think really the biggest problem is that users of this system, they want something that looks like a database. They don't want a misfit file system and two functional programming abstractions. That's not really going to fly with people who had been using MySQL or Oracle or something like that. So really, I think a way of, I've got a list here of problems, but I think it can all really be summarized by people want something that looks like a database, but they want something that performs better than a database. They want something that's more flexible than a database. So this was the problem that confronted people at Facebook around 2007. They had infrastructure that was really based around MySQL, and they had managed to hire the top sort of MySQL technical talent in the world at that time. And even with all of these incredibly smart people on staff nursing these sharded MySQL systems 24 hours a day, they still had systems that were spontaneously combusting. And they knew that, at that point, their data needs were growing every day, just sort of hockey sticking upwards. And they quickly understood that this was not a system that they could keep running much longer. And they learned about Hadoop, and they realized that this, could be the answer to their problems. But they also knew that the analysts that they had on staff, the people who were actually trying to derive insights from this data, who were used to using SQL, who were used to using MySQL, were going to revolt if they were instead told, well, hey, you can still analyze the data, it's great, it scales, but you need to write a MapReduce job instead of a SQL query. So what they built was a system called Hive. And I think a lot of people have heard of it at this point, and a lot of people understand it as a SQL to MapReduce compiler and execution engine. And that's definitely accurate. That's one of the major features that it provides. But I don't think it gives Hive enough credit for all of its contributions. And I think in some ways, the biggest contribution that Hive has made, and the one that I think is really the lasting contribution, is Hive's take on metadata. Because schemas in the context of relational databases, traditional relational databases have these problems, right? I mean, they're kind of like handcuffs in the sense that you have to decide what the schema is before you analyze the data. It's a high-stakes game and stuff like that. It is effectively schema-on-write. Before you write the data into the database, you need to figure out what the schema is. Hive turned that equation around and said, let's project schemas, let's project logical structure onto unstructured and multi-structured data, regardless of the format, at read time. And the cool part about this is, first of all, you don't have to wait for a DBA or whoever it is in your organization who's the controller of the schema to load your data. There is no load step at this point. There's only a read step. But another cool aspect of it is there's no reason why you can't project multiple schemas onto the same data. There's no reason why I can't project one view and you another view. So it introduces this amazing level of flexibility. It also, since the logical view of data is completely decoupled from the underlying storage layer, it's possible that you have a single table which actually maps to files in a variety of different formats. So one use case that's pretty interesting is maybe data arrives in HDFS in an unoptimized format, let's say CSV, or it's just Apache log files or something like that, and you can start querying it the second the write to HDFS finishes, but maybe in the background you have a task which is incrementally converting from the ingest format to an optimized format. But you don't have to wait for that to complete. It's just like your queries incrementally start running faster and faster as this background translation process completes. So there's some pretty interesting use cases that this sort of new way of working with data has made possible. On the other hand, though, Hive does have some drawbacks. And I think one way of sort of summarizing the first list of drawbacks is to say that a database is more than just a query execution engine. It's more than just a SQL engine. It's also a collection of user-defined functions. It's also full support for SQL. It is administration and security and authorization. All of these things, like file systems, you say the word file system, people automatically imagine a set of features. You say database, and people automatically imagine an even larger set of features. And the amount of time it takes to implement all of that stuff from scratch is bewildering. So my experience working on Hive was you would implement one feature and expect people to say thanks, and instead they would say, what about these 5 other features that you guys still promised would be here? So that's one problem. It's not an insurmountable problem, it just takes time. The bigger problem with Hive is its dependency on MapReduce. So MapReduce is a compromise. And the compromise basically is we will give you a system that can scale to petabytes of data, that can do joins across petabytes of data, and it will finish eventually. But if you are trying to run a job against a sliver of data, let's say a megabyte, it's still going to take 30 seconds to complete. Something that on a single node, SQLite instance running on your laptop should take like half a second, maybe even less. It's still going to take 30 seconds on MapReduce because of all of this overhead of spinning up tasks, managing those, and things like that. And this is, I think, really the biggest complaint that I've heard from people who use Hive. Why do my small queries take 30 seconds to run? And this is really a big deal because it kills the ability to sort of do this sort of like interactive querying and data discovery and the sort of thing. So if you know what the queries are that you want to run in advance, if you already know what the data looks like, then it's fine. But if you're analyzing data that you've only just received and you want to just try to get a rough idea of what's going on, you probably want to run like 10, 20 queries, you know, in 10 minutes, right? Just to get a very rough idea, and Hive really makes that impossible. So recently, a lot of energy has focused on ways of sort of combining or merging the good things about Hive, the good things about Hadoop, while alleviating the drawback, and primarily the drawback of latency. So one thing that's emerged recently is the Stinger initiative, and the goal of this is to make Hive faster. And they're sort of splitting that into 3 different things. So one is adding a columnar query engine for Hive. And the idea is instead of having a query engine that goes a row at a time, this engine would extract large blocks of rows and then process them a column at a time. And by doing you know, pretty standard techniques like loop unrolling, trying to be more cache aware, you can extract a lot of performance benefits from that. And going hand in hand with that is also the design of a new column-oriented file format called orc-file, which is in many ways sort of the successor to RC file, which had been a format designed at Facebook. And then most significantly is the TES project, which aims to replace MapReduce with what is in effect an improved version of MapReduce, which eliminates some of the overhead found in MapReduce. It also allows you, in many cases, to avoid sort of the forced materialization to disk step that you see otherwise in between the map and reduce stages. So I think all of these efforts show a great deal of promise, but for the rest of this presentation, I wanted to focus on things that are available right now, systems that you can use immediately, basically to get around this latency problem. So one of the first approaches that we saw to this issue was basically taking an MPP database and running it on top of Hadoop. And a lot of vendors have introduced Hadoop connectors over the past 2 years. And the basic idea is you have your MPP cluster, you know, on one side of the data center, and you have your Hadoop cluster on the other. And using software connectors, you're able to read data off of the HDFS nodes over to the MPP cluster and process them there. The problem with this approach is that we're still sort of violating one of the core tenets of Hadoop. And that is that we're no longer pushing the work over to the data. We're now back to the same old model of pulling the data over to the work. And in some of these systems, it's even a little bit worse because we've also still added in that load and convert stage. Not only are we pulling the data over, but we're actually converting it into the native internal format of the MPP database, you know, before it can run. And if you're willing, you know, to have a system that can't quite scale the way that Hadoop does, that sacrifices that, and which also can't analyze data without first of all converting it, then I think there are benefits to this approach. MPP databases have really good performance, and they get that performance by being able to organize data in a very specific way. So there are benefits to MPP databases, but it's not a very good approach to sort of the new paradigm of Hadoop. But on the other hand, I think looking at this diagram, you can sort of get a hint of how we can fix this issue. And it's basically by taking the same ideas, the same technology that we've seen in MPP databases that people have spent 20 years working on, distributed join algorithms, relational operator algorithms, things like that, leveraging that same technology, but running it in a data local fashion. So in effect, taking every process that had been running on an MPP worker node and now co-locating it on an HDFS data node. And that allows us to eliminate that I/O bottleneck that sits between the worker and the storage tier because we've eliminated the distinction between the two. But I also don't want to leave people with the impression that building a system like this is as simple as just taking an existing MPP database and taking the process that you had been running on the MPP worker node and now running it on the HDFS data node. Because it's not that simple, and the major distinction is that the query planner that basically takes a query from the user and farms that query out in a modified form to all of the worker nodes, it needs to be block aware. It needs to understand where the data sits on the data nodes in order to craft a query plan that limits the amount of data that needs to transfer between those nodes. Without that, you still have that bottleneck, except now instead of existing between the MPP cluster and the HDFS cluster, the bottleneck exists between individual HDFS data nodes. So to sort of summarize what I think defines this new approach to scalable analytic databases on Hadoop, first of all, and this is sort of the core idea, we are maintaining data locality. So we have a distributed query planner that knows where the blocks sit in HDFS, and it's able to use that information to optimize the query plan that it generates. And the other benefit, the other thing that sort of defines this is that by combining existing relational techniques, or existing database techniques with Hadoop, we're able to get better, lower latency, more real-time performance out of the resulting system. But we also want to combine it with the flexibility that Hive introduced. So this new group of systems that we've seen emerge, one other thing that they all share in common is that they support schema-on-read. So they're basically storage format agnostic. They don't say that you need your data to be in any given format. They will say that if you put it in one format over another, it probably will lead to better performance, but they don't make a hard demand that it specifically be loaded first. And I think the other thing that really defines this set of tools is that externally they look like a traditional database, which makes them compatible with this whole ecosystem of tools that have evolved over the past 20 years that run on top of relational databases. And I think that's really one of the important things to say about SQL. SQL is not in many ways the most convenient language to use. We've seen, for example, there are other high-level sort of domain-specific languages that you can run on top of Hadoop. But I think the benefit of SQL is that SQL is really sort of like the Esperanto of data analysis, except everyone actually sort of speaks SQL. And the other, I think, benefit is that if there are drawbacks to it, if there are problems with it, at least we know what those problems are. And there's a lot of sort of institutional wisdom about how to work around them. So in terms of the new systems that sort of fall into this category, over the past 18 months, a handful of them have been announced. Some of them are already being used in production. I think the thing that really sort of inspired these systems would be Google Dremel, which was sort of announced to the wider world in a paper that was published in 2011. And I think Dremel's contribution was sort of twofold. One thing Dremel did was it sort of gave an example of a company that had built a system that allowed people to basically run relational queries across petabytes of data that was scalable to an extent that far outstripped what people had seen up to that point using traditional MPP databases. And I think it sort of inspired people, it almost in a sense gave people courage to then go and try to design similar systems. And then this other big contribution was the way that it handled nested read-only data. So there was sort of a subsection in the paper that described a way of handling or of shredding, columnizing nested data, which we've seen reflected in some of these new open source file formats like ORCFile and Parquet. And that's a really big deal, I think, for some of these, let's say, web companies or companies that are trying to analyze large streams of events, because oftentimes those events are actually heavily nested data. And this is a quite convenient feature. Instead of having a schema which is 1,000 columns wide, you can have a schema which effectively stores structured records. So another system that was introduced is Apache Drill, which is sort of aiming to be an open source implementation of Dremel in a similar manner that Hadoop is an open source implementation of MapReduce and GFS. So Drill is implemented in Java, and at this point it's still a work in progress. Another system that was introduced is Cloudera Impala. So Impala is in addition to being influenced by Drill, it's also heavily influenced by MonetDB and X100. So these were research projects which basically tried to, or were successful in re-architecting an analytic query engine to take advantage of some of the parallelism which was capable or available in modern processors using SIMD instructions. So basically for every cycle of the machine, when you load data into a register, you're actually able to split that word into multiple segments. So you, in effect, get like 4 cycles or 4 operations per cycle. So folks have probably heard of SSE2, which was one of the new sort of like instruction sets that was introduced in an Intel processor, and that's sort of the core idea there. It's very similar to, in a way, what you saw in Cray vector processors, the same idea. And then the other system would be CitusDB. So this differs a little bit from the other systems in the sense that it's built on top of PostgreSQL, using that as a starting point. And I think the benefit there is that you know, we're able to sort of leverage a lot of existing work that's already been done and be able to focus more exclusively on the elements that you know, really do need to be written from scratch, like the distributed query planner, and yet still take advantage of all of the sort of tools that sit around the query execution engine. So I wanted to go into a bit more detail about the specifics of how these systems are implemented. And since I'm most familiar with CitusDB, I'm going to use that to sort of illustrate these concepts. So this is a high-level block diagram of CitusDB. So off to the left top side, we have the clients, which in this case could be the PostgreSQL, pSQL CLI, or an ODBC or JDBC client. To the outside world, CitusDB looks like Postgres. So we're compatible with all of the tools that are already compatible with Postgres. On the right-hand side, we have Hadoop's metadata repository. So in this case, the HDFS name node, also the Hive metastore. In the center at the top, we have the distributed query planner. And along the bottom, we have the HDFS name nodes with the addition of the CitusDB worker processes, which are effectively an almost unmodified version of PostgreSQL. So before a query is received from a client as sort of an offline step, we synchronize the metadata, the file system metadata, off of the HDFS name node. And we do this so that when a query is received from the client, we don't have to incur sort of the latency overhead of also going to the name node and fetching the relevant metadata before being able to handle the query. So for every HDFS block in the underlying file system, we take advantage of a feature that was recently introduced in PostgreSQL called foreign data wrappers. And I don't know if some of you are familiar with Hive. Hive has a pluggable API called CerDes, which are basically the pluggable storage format layer. And foreign data wrappers are PostgreSQL's equivalent of that, except they also support some features in addition to what you find in CerDes, like the ability to push filters down to the underlying storage layer, which is a pretty significant benefit. So when a query is received from a client, the distributed query planner rewrites that query into a set of fragment queries. And these fragment queries, one per HDFS block, are farmed out to the various CitusDB worker processes that are running on each of the data nodes. And the worker processes execute these fragment queries. Once that's complete, they then return the results back to the coordinator node where they're merged together, and finally return to the client. So I wanted to go into a little detail about why we chose to use PostgreSQL as the foundation of this system. And I think, first of all, you know, I'm an engineer, and I want to talk a little bit about, from an engineering standpoint, why I think this choice made a lot of sense. So one thing that can be said about Postgres is it's very cleanly designed. It's very well laid out. The people who have spent many years building it, I think, have showed a lot of sort of self-control. They've taken a very measured approach to building sort of a solid, easily extensible system. Another benefit of PostgreSQL is that there are many well-defined public APIs that allow us to extend it in a fashion where we don't have to fork it. And I think one of the trends that we saw in the last decade was that a lot of MPP database companies use PostgreSQL as the foundation of their system, but very early on they would fork it and really never join back up with mainline PostgreSQL. We think that in the last couple of years, PostgreSQL has developed to a point where it's no longer necessary to actually fork the code base if you want to develop a distributed system on top of it. And so far, having worked on CitusDB for 2 years, we've been able to keep pace with each new version of PostgreSQL as it's introduced. And I think really the benefit for our customers is that we see PostgreSQL as a feature of CitusDB. And we want to keep pace with PostgreSQL so that as new features are introduced in PostgreSQL, we're able to provide those same features to our users. So we're taking advantage of those plugin and extension APIs, and we're also able to make available to CitusDB users a bunch of the extensions that are already available in core PostgreSQL. And these include PostGIS, which is their geospatial extension, a full text search extension, support for JSON. And also, I think, and this is particularly significant to enterprise customers, we also are able to support, thanks to Postgres, a lot of sort of enterprise features like ODBC and JDBC connectivity, internationalization, and security and administration functionality. So it really means that, like, thanks to the work that's already been done by the community, we're able to provide all of these features that people really expect to have available when you say the word database. So just to quickly summarize, what's going on with this new sort of generation of databases, I think the first thing is these systems provide SQL, because SQL is what people expect, and it's what this whole industry is sort of built around. But we're combining that with real-time responsiveness. We're working around some of the problems that exist with MapReduce by replacing MapReduce with our own custom query execution engine and query operators on each one of the worker nodes. But at the same time, we're maintaining the core benefit of Hadoop, data locality, which is what fundamentally allows Hadoop to scale out. But we're also providing and maintaining the same level of flexibility that Hive provided by allowing you to do schema-on-read to process data in a variety of different formats, and is also to extend the system to support new formats. So at this point, if you're interested in giving this software a try, you can go to our website and download it. We have packages available for RHEL and CentOS, and we also have an EC2 AMI. So if you're interested in quickly spinning up a cluster and giving it a go, that's possible too. And the URL for that is available there. And I also wanted to say that we're hiring. We're really interested in finding people who are interested in hacking on databases, PostgreSQL in particular, who are interested in working on open source systems. So if that describes you, I strongly encourage you to give us a ring. That marks the end of this presentation. So if folks would like to ask questions, I think I have 1 minute and 52 seconds to answer them. Yes?
I assume you are converting the data from flat structure to a column structure in your flat wrapper?
No, we're not. We're not doing that. So if data exists basically in a, let's say, flat format like CSV, we process it as CSV. It would be, you could convert it to a more optimized columnar format in the background. And in that case, if a foreign data wrapper is available for that format, then we support that as well.
If it is not, data is not in CSV, it's, say, some log record, web log record, which doesn't have any CSV format, but a string of bytes, you'll be able to process that, or you need a pre-processing that?
So we basically can process it if there is a foreign data wrapper available for it. So we're
somebody has to provide you foreign data wrapper?
It's like Hive, and it's like all of these other systems in the sense that they are format agnostic, but that being format agnostic basically means that we're able to handle data as long as a plugin, as long as a reader for that data format exists. But I think the important thing is that these are public APIs. So it is possible, let's say that you have some bizarre format that is unique to your organization, you do have the ability to go and implement your own reader. There are also sort of like hacks. We're working on a regular expression foreign data wrapper, so you would very easily be able to, for example, extract information from Apache weblogs or something like that. It's not, in terms of performance, it's not optimal, but it does allow you to quickly, let's say in the background, convert to a more optimal format.
The other question I have is that in order to make use of Postgres cost-based optimizer,
yes, we do.
how you're collecting the statistics of the data? I mean, you're scanning periodically and gathering max, min, frequency counts, etc.?
Yeah, so that's part of it. At the moment, we're for the most part, basing it on file size. That's one of the main things. But we also do a scan and collect statistics that way. But it's a pluggable architecture, so we are not, we don't really need to make any changes to the existing cost-based optimizer in order to harness the work that's gone into it.
Because file size does not give you the frequency distribution. It does not allow you to do the optimization.
It's the API. So just to answer it, basically the foreign data wrappers also have an API to collect a sample, like a random sample of rows. And then we do collect that just as a regular PostgreSQL database would. And then we give it to PostgreSQL. It creates its histograms, it creates its frequency counts, and then keeps it in a PG stat table. So it's just that there is an API in foreign data wrappers. If you implement that API to collect a random sample of rows, then yeah, we'll make use of that.
Question?
Yeah.
On the Postgres compatibility, with the explain plans, would they be, if you looked at an explain, would it be relevant to the query like it would be if looking at a normal Postgres database? Is that how you would use, figure out optimization techniques or changes to your query to improve performance?
Yeah, so as my coworker Özgun mentioned, the foreign data wrapper API does have a mechanism built into it for collecting statistics from the underlying data set. So we're able to feed that into the optimizer, and then you would see that corresponding information in the explain plan.
Cool.
Yep.
Yay. That's it.
Okay, that's it, I'm told. Thank you.